Okay, hello everyone. Welcome to the second special seminar on numerical and algebraic geometry. This seminar is being organized by Institute for Mathematical Sciences of Americas at University of Miami. It's our pleasure to have our second speaker here, Professor Vladmir Baranovsky from UC Irvine. As it is the theme of the seminar, I give a very brief introduction of the speaker. So Vladimir finished his PhD in pure mathematics in the year 2000 at the University of Chicago under Victor Ginsburg. Later, he did some postdoctoral studies for half a year at Institute for Advanced Study in Princeton, and then he moved to Caltech, and he was at Caltech from 2001 to 2004. And at 2004, he became assistant professor at UC Irvine, and ever since he has stayed there. And nowadays, he is a professor in the math department at UC Irvine. Vladimir's research interest is algebraic geometry and representation theory. It's truly an honor to have Vladimir here. And with that said, I would like to let Vladimir start his talk on mapping spaces and E2 algebras. Vladimir.
Thank you. Thank you so much for inviting me. It's a pity I didn't fly in person. It's although California is supposed to be warm as well, but not at the moment. And also, so most of the talk I will actually spend on discussing not the mapping spaces, but other spaces which I expect to be closely related to them. And so just one conjecture that I wanted to state towards the end still needs to be repaired, but I will clarify what is happening. And eventually the goal is to move from topology to maybe to algebraic geometry, and I will also clarify in what direction. So yeah, so I will start on the topological side, and I will choose M, which is a compact oriented manifold, and so I will be discussing some problems which are related to its cochain algebra. So this is the topological setting, but eventually, of course, I would like the whole technology to be in the condition when this cochain algebra can be replaced by a category and maybe a category of sheaves on an algebraic variety or vector bundles on algebraic variety. But topological model is a nice model to play with. And another ingredient in the most of the talk today will be a graph. And I'll assume that the vertices of the graph are labeled by numbers 1 through n, and so there is a E, which will be a set of edges. So I will start by considering what is called the graph configuration space, and for this it's convenient to assume that this graph has no loops. So loop would be an edge which starts and ends at the same vertex, and no multiple edges. So we don't want anything of this type. So if that's the assumption on the graph, then let's consider what is called the graph configuration space. So this will be, we'll start with the n-fold Cartesian product of our manifold, and then we remove a union of diagonals. So with the usual configuration space, we would take all possible double diagonals and we remove them. And in this case, the graph will tell us that we're removing maybe only some, but not others. So let's say that DE, for any edge in our graph, DE will be diagonal. which looks at points in our n-fold Cartesian product. And we require that xi is equal to xj if our specific edge E connects the vertex I and j in our graph. Right. Okay. So if the graph was the complete graph on n vertices, we would be dealing with the usual configuration space. And here we have a modification with we just throw out some double diagonals, but not the others, right? So one possible topological task would be to try to compute the maybe not at first relative cohomology of this n-fold Cartesian product, and let's say that the union of all of these double diagonals, I will just call it by dg. And so I understand it as a boundary that gets removed. And so suppose we want to construct some kind of model that computes cohomology of relative cohomology at first. And we also say that if we started with a compact-oriented manifold, then the relative cohomology by Lefschetz duality can be identified with homology up to certain shifts of this complement of this graph configuration space. So this is the last statement is by Lefschetz duality. So okay, so how do we approach computing this? And we could just say that the approach would be based on kind of upgraded version of inclusion-exclusion formula. So we're removing a union of diagonals, and we could just say, let's pretend first we're removing disjoint union of the diagonals, but then remember that there are double intersections of these diagonals. Then we take into account triple intersection of these diagonals and so on. So there is a standard topological argument that says that this relative cohomology can be computed by a complex which and you will see where inclusion-exclusion comes up. So we would start with the complex that computes cohomology of Mn. And so I will just drop the z coefficients. So these are just usual normalized complex of simplicial cochains with integral coefficients. And so then we say, well, but there is this boundary that we are trying to throw out.
Can I ask you a question, Vladimir?
Yes.
The union
yes,
of these DEs you call D of G.
Yes.
And then where is the double intersection of the diagonals? Is it what is?
Yeah, we'll see in a second. Yeah.
Oh, okay.
So so at first we start with the cochains on the Cartesian power, and then we say, well, we wanted to remove all double diagonals. So each of the double diagonals, we can say that each of the double diagonals can be identified with a Cartesian product Mn minus 1, because we have simply identified xi and xj, and it's embedded into our n-fold Cartesian product. And so we could say that to compute to start constructing the complex, we in some sense remove, but in fact we just looking at the cone of this map into c dot n minus 1, where the sum runs through all possible edges in E. So this is kind of like removing each of the double diagonals. So let me just write that dg is the union of dE. Okay. So now, but now we say, well, that's not likely to give the correct answer because there are double intersections. So what do we do? Well, we take them into account. Now we say that there will be the next term in this complex, there will be a sum over pairs of edges. And then there will be cochains on DE1 intersection with DE2. And then we want to keep going. And then in some position I, we would have direct sum over all subsets in the edges, subsets of cardinality equal to I. And so then we would take cochains at this iterated intersection of the diagonals. So it will be, so we're intersecting D, E over all edges in our subset. Okay. Okay. And so the arrows are fairly straightforward combinatorial arrows induced by the embedding of iterated intersections of the diagonals into the diagonals themselves, and so on. Now, we can also say that this intersection of double diagonals over a certain set of edges. So this can be identified with a Cartesian power, but of some degree that depends on the choice of a subset. And let me just give a simple example of a graph with 4 vertices. So it will be maybe 1, 2, 3, and then 4. And so if we're looking at these edges, we could start at the diagonal that corresponds to the edge from 1 to 2. So this will be the edge E1, and then there will be edge E2, and then we'll be adding to the subset edge E3. And so what happens in this case? Before adding any edges, we're dealing with the fourfold Cartesian product, and then we're looking at the diagonal corresponding to E1, and we say because the first entry is now equal to the second entry, this is not a fourfold product, it's a cube, Cartesian cube. But then when we start intersecting this with the diagonal of E2, then we say, well, the first 3 entries are equal to each other. The big deal here is that if we're looking at further intersection with the diagonal of E3, no further conditions are imposed. We're still requiring the 3 points to be equal to each other. Right. So this is why as we're throwing in one extra edge, sometimes so our exponent of the Cartesian power changes, sometimes it doesn't change at all. Yeah. Okay, so let me just rewrite the complex that we're getting that computes this relative cohomology. It starts again with CMN, and then it goes, let me just rewrite as subsets of edges with cardinality equal to 1, and then there will be cochains on M. Well, it's n minus 1 at this step, but as we go along, as we reach step I, we will be looking at the subset with I edges, and there will be cochains of M, L of S, right? Right. Okay. So, and at this point, so this complex does compute the relative cohomology. So, so this is just a standard topological argument. Again, what do the arrows do? The arrows take a subset inside E, and then they attempt to throw in additional edge to the subset if that all edges that are not included into S yet. And because then some Cartesian powers end up embedded into other Cartesian powers, so the arrows are just the map in the opposite direction on the cochains that you're getting. Okay. But now, so as it sometimes happens in topology, we would say, okay, what if we wanted to interpret all of this construction in terms of, so we want in terms terms of just C of M. And we kind of want to say that whenever we have cochains on the Cartesian power, they have something to do with cochains of M, and then the usual tensor power to the k. Right. So there is a standard Eilenberg-Zilber contraction. So originally it was designed for 2 factors, but you can iterate it to k factors. And in a way, you could say that when you're just shrinking a large complex of cochains on the Cartesian power to a smaller complex of the k tensor power. All right. Now, the issue that comes up here is that, so these 2 complexes are, of course, different, and the one on the left is the larger one, and then there is a contracting homotopy, and it's fairly difficult combinatorially to deal with the homotopy on the left-hand side. And now, so before shrinking these vector spaces, things worked very, very nicely. But now let's see what is going on. So suppose we are looking at the simplest case when M gets embedded by the usual diagonal M times M. And so what happens on the level of cochains? We, of course, have the pullback, but then if we wanted to shrink them to tensor powers, we would say, well, it induces a map from cochains on M, and then back to cochains on M. And so this is, of course, the standard multiplication on cochains, on topological cochains. But this standard multiplication is not commutative. And this will be a big deal. So this non-commutativity is also reflected just in the fact that this quasi-isomorphism between these 2 complexes are not quite compatible with the symmetric group action, right? So in the end, this will be a problem. So let's see what is going on. Why would that be an issue when we try to shrink? So so suppose we have a graph with just 3 vertices, 1, 2, and 3, and then it means that we have started with the Cartesian cube of our manifold, and then we said we have points x1, x2, and x3. Then we're imposing the condition that maybe at first x1 equals to x2, and then x1 equals to x3, or we can impose in the opposite direction. On the level of the on the left hand side, so this works perfectly fine. But if we try to replace by tensor powers of cochains on M, so we see that these arrows in our complex, they are built out of multiplications of cochains. And so when we compute, so when we are computing, so if we take this combinatorial part of this differential delta, so delta squared, so there will be terms where you started with a triple tensor product, A1, A2, A3, and then you're ending up with A1, A2, A3 minus A1, A3, A2. If we were dealing with the commutative algebra computing the cohomology, that would cancel, and then the differential would be actually squaring to 0. But if we wanted to insert cochains, then we would be in trouble. So this delta squared is not equal to 0. So we could try to resolve the difficulty by replacing C star with some commutative algebra that computes the cohomology. So can replace C dot M, for example, by differential forms. right? So, and it works, and in fact, this version of the complex was computed, so this construction was done by Helmi, Guizon, and Rong. So this, they did it for arbitrary graph in relation with not invariance. And also a version of this was earlier done by Bendersky and Gitler, that were studying just the usual configuration spaces. So when the graph is just complete graph and then vertices. Okay. So now what do we do if we don't want to pass to differential forms? For instance, if we care about torsion in integral cohomology or relative cohomology, if we are not ready to just to go to characteristic zero coefficients. Right. So again, the problem is that cochains on M, so, these are algebra, and this DG algebra. Associativity works very nicely, but commutativity doesn't work. And what helps us is a construction by McClure and Smith. So they used it for when we are studying these cochain operations in general. So what they discovered is that there are operations actually with n inputs and with a single output labeled by surjections pi from a finite set of just numbers between 1 and n plus d, and then landing into the set with 1n. Okay, so we want surjective maps. We write them as sequence of values. So write those maps, those as sequences of values. So in a short while, we'll be considering a surjection that we'll label as 1 to 1. So it means that a set, so 1 to 1 means that a set of size 3 surjects onto a set of size 2, and the values in this natural order are, well, 1 to 1. Okay. And now, so I'd rather not give a general definition of what these are, but there are some nice cases. So suppose when d is equal to 0, so in that case we have a surjection from a set with n elements to a set with n elements. So we're just dealing with permutations. So each pi is a permutation. And in this case, the operation is easy. You take this permutation. So we have this input when we have an ordered sequence of elements in C of M. We can permute that sequence and then apply the usual associative product. So, for instance, we would just say that operation 1, 2, if it gets applied to A1 tensor A2, so that gives A1, A2. And if we have operation 2, 1, then we have we need to swap the order of the factors and compute A2, A1. Right. Okay. So, and it's clear that for any permutation, we have such an operation. Now, there is a case of operation 1 to 1. So 1 to 1. It gives a homotopy, between 1, 2 and 2, 1. And so this is what, of course, Steenrod operations are about. So they would discover it as something that you can do on cochains if you want the homotopy between these two things. And if you're computing things in characteristic 0, say rational cohomology, these operations disappear. You don't see them on the level of cohomology. But if you're working with integral things, then they actually remain and they become important. Now, so let me just give an illustration of what sort of operations we're talking about. So suppose we wanted to compute one-to-one evaluated A1 tensor A2. A1 and A2 are both cochains. So you can, it's something that you can evaluate on singular simplices. Now, suppose you want, so the result of this operation will be a cochain, and you're expected to evaluate it on simplices. And suppose, let me just write 1, 2, 3, 4, 5, 6, 7. Right? So suppose you have a simplex with 7 vertices, and you want to just describe what this cochain will do. So the value will be a summation with certain signs. And let me just explain just a particular term, and then we'll see that it's generalizable. So first, the sequence 1 to 1 has 3 terms, and we take this set of 7, or actually 8 vertices of the simplex, and we produce an overlapping partition into 3 different blocks. Overlapping partition meaning that I take the set of vertices, I have the first piece vertices from 0 to 3, then there is overlap, 3 is included into the next subset, 3, 4, 5 is the next one, and then 5, 6, 7 is the next one. Okay, so now so I'm splitting my set of vertices into 3 different pieces in all possible ways. Then my sequence was 1 to 1, so I will write 1 to 1, so corresponding values over the pieces of this partition. And then the next thing I can say, so 1 is standing over what? Over the subset of 0, 1, 2, 3, and then it's also standing over 5, 6, 7. So I can take all of these vertices, and essentially I have skipped the vertex 4, and with the remaining vertices, I can still span a simplex of a smaller dimension. And then number 2 is standing over vertices 3, 4, 5, and they span a simplex, and then I can compute the value of A2 over that, right? So and then there is summation over all possible ways to break our interval into 3 different pieces, and I will not explain in the science. But that's roughly the nature of what is going on with these cochain operations. And so every surjection will generate something like that. All right. So now, so solution to the problem that delta squared is not equal to 0. If we were trying to build this complex again with subsets of edges, so we have cochains of M, and then we would want to replace it by certain tensor powers depending on S, right? So so solution to this problem is this. So these arrows are used to add edges to S. So we would take a single edge that's not included into S yet and just append that, and that's how these horizontal arrows would go. So we say now add subtrees, connected subtrees of G as well. So connected subtrees as well. And then each subtree will generate McClure and Smith operation. So what used to be the case is when we are adding an edge, so this this tensor power decreases by 1, but what we are doing, we're taking two tensor factors, we're just multiplying them as cochains, and so the result then lands into a tensor product of degree, the previous degree minus 1. So here we're not adding a single edge, we're adding a certain subtree, a connected subtree, and then maybe instead of 3 or 4 different tensor products, we'll feed them into one operation, and then we will take one output. And so how does this go? So let me just write very briefly what the rule for that assigns subtree to operations. So we say assume subtree is on vertices 1, 2 up to k. Maybe there are we can always renumber to achieve this 1 to k, and then proceed by induction. So when in the case when we are actually, if the edge was connecting 1 and 2, we're adding the operation 1, 2. So that means the product in this particular order. And now, so we again, the trees that we will be adding, I'm skipping this detail, but the trees will have this this nice property that if we try to see the vertices from 1 to s, how are they connected? So the vertices from 1 up to s should also form a single connected subtree. So what's happening when we proceeding by induction? So if we have a tree that involves vertices from 1 up to k minus 1, then we want to throw in additional vertex k, and so there will be an edge that connects k with something in here, and then let L be that that other vertex on the other end. So again, inductively, we're adding this vertex number k, and in this case, look at sequences that appear from a subtree on 1 up to k minus 1, and then in each consider those x which are on the right of all occurrences of L, on the right of all occurrences of L, and then replace x by x, k, x. So let me just illustrate what's going on with a simple tree where 1, 2, 3, and 4. Right. So we think of this as built out of a subtree that includes only 1 and 2. Then we're adding vertex 3. Then we're adding vertex 4. So originally we start with 1 and 2, and the sequence is 1, 2. So that's the product operation we started with. So then we're thrown in 3, and 3 gets connected to L equal to 1. So it means that we are bothered about this last occurrence of 1, and then we'll look at everything to the right of it, and if x is that value, we can replace it by x, 3x. So in this case, there is only one thing we can do. We're replacing 2 by 1, 2, 3, 2. And then once we've done that, we say, well, now we are throwing in vertex, vertex number 4, it's still connected to the value L equals 1. But now candidates for X are just everything that stands on the right-hand side of the last occurrence of 1. So there are actually 3 candidates for this replacement. And again, with certain signs. So we are getting 1, 2, 4, 2, 3, 2, and then plus minus 1, 2, 3, 4, 3, 2, plus minus 1, 2, 3, 2, 4, 2, right? So this kind of inductive procedure, and so each of those, each term in that sum will give a certain operation with 4 inputs and a single output, and it will have some non-trivial homological degree. So in this case, homological degree is -2. So these are the operations that you would use to correct the complex that you're trying to construct. Again, you're trying to compute homology of configuration spaces. And so this sort of formula was conjectured. So it was conjecture. So by myself and Maxim Zubkov in 2017. So we described this complex, and so there is a certain detail about the sequences, and let me maybe first mention it here, that sequences that come up as a result, then they can contain a subsequence of the type I, J, I. So if we take 2 values, I and J, any 2 values, there could be a subsequence I, J, I, or J, I, J, but not I, J, I, J, or J, I, J, I. So as we move, for instance, we could pay attention to maybe values 2 and 4, and we see that we're in the subsequence, for example, in the middle one, we have 2, 4, 2, so that's allowed, but we never see 2, 4, 2, 4 as a subsequence of that. Now, this is important because, in a sense, we're proving that we can get by not with all operations of Maclaurin-Smith, but the ones that have this property for subsequences that I just stated. And I will mention in a second why that's important. So the conjecture is that with these specific operations that allow to correct the differential, so the corrected differential, it satisfies, of course, as delta squared is equal to 0, and it computes cohomology of relative cohomology Mn and then dg, which is also homology of this configuration space that I was mentioning. And so it was proved, some cases were proved by Matthew Levy in his thesis in 2021. And so he did a fairly difficult computation involving Cartesian products and tensor powers of cochains. And so he's proving that this is true for n, the number of vertices less or equal to 5. Right. So he worked out a certain computational machine that kind of exhibits these operations on the level of cochains. Now, so let me just write it as a remark. And so we can replace cochains on M. So what did we want from M to describe this complex? We know that it is an associative DG algebra, and so that is used in the definition. We also said that we are using these Maclaurin-Smith operations, but then it turned out that not all of them, but some of them. We can replace these cochains by an algebra, algebra A over E2 operad. So it's not my intention to go into operads and algebras over operads, but let me just say that it's, well, for our purposes, they're associative DG algebras with additional operations, and so operations that, and there are different actually realizations on what sort of structure we could call an E2 algebra, but for our purposes, it's the action of these sequences of that specific type, that iji is allowed, but ij is not allowed. So this is, again, something that was observed by Maclaurin-Smith, that you have this filtration on the operations, and then this is a filtered piece which realizes the E2 operand. Okay, so at this point, it means that we could try to forget the manifold. We could just work with this algebra, which is associative and only commutative up to homotopy, and we could also attempt to maybe to start with a category which has some structure, and then construct this coefficient algebra A out of a category. Okay, so now let me just briefly, only have, I guess, 7 or 8 minutes, indicate what is the relation with mapping spaces. So relation with mapping spaces. So suppose we wanted to look at maps from a simplicial complex K into, say, our target manifold M, and simplicial complex will have sets of vertices, edges, and then the usual arrows between them. And then we could say, let's look at the maps from vertices into M, and that's obviously a Cartesian power. And then because maps are contravariant, so the arrows would reverse. And we eventually say we would like to compute cohomology of those. So we need to apply some standard functor, for example, like cochains, which is again contravariant. And so we would just get some kind of object, cochains on M K0, and then cochains on M to the power K1. So K0, K1, K2, they're maybe a finite sets. So we're just looking at the finite Cartesian powers, essentially. And so up to this point, it all works very, very nicely. And then if you tried to construct a complex out of this simplicial object, then it would, under certain assumptions, so you need some convergence assumptions. But you would be computing cohomology of the maps space. Now, for example, when K is a circle, you would be looking at cohomology for the space of loops in M. Okay, but now you try to play the same game, and it will be with the same difficulty as before. So we want to replace just cochains on the Cartesian power by usual cochains taken to some kind of tensor power. Okay. So this is a quasi-isomorphic space, but again, if we wanted to establish contracting homotopy, one issue would be with lack of symmetry, and so it does complicate this project. What is the project? So we had this complex that computes a cohomology of the mapping space. We want to shrink it down. We want to write it in terms of something that only speaks using the cochains of M. And what's the problem here? So for instance, if you take a point in K0, so this is a vertex in our simplicial set, and maybe there are several edges that are coming out of it. And so how do the arrows work in our complex? How do the arrows work in our complex? Well, what's happening is maybe we have 3 edges coming out of the vertex, and they're labeled by A, B, and C. And we want to say that when we are looking at one of these arrows, or one of the boundary arrows, so we'd want to send A tensor, B tensor, C simply to their product, right? So this is something that would make sense if we wanted to do this, to shrink it. But to compute the product ABC, we need to choose order of the product. And one way would be to say, well, choose some kind of order between the edges and stick with this. And it works if we are dealing, instead of cochains, with something that's graded commutative, such as differential forms. And there was a paper in that direction by Jones and Gitler, and maybe there was a third co-author that were studying loop spaces from this point of view. But if you are dealing with cochains which are not commutative, then really you have exactly the same kind of problem as with graph configuration spaces. That once you're replacing cochains on the Cartesian product by something smaller, so you're using cochains which don't have commutativity. And so let me just state the result if K comes from a graph, so the differential on the smaller complex, so it will be a C dot M tensor K0. So there will be a differential C dot M tensor K1 and so on. Can be defined using E2 operations of Maclaurin-Smith on C dot M. So and the operations are defined in pretty much the same way. So instead of before that we had some kind of graphs that got converted into operations, and so in my version of the statement, the graphs will be just on the sequences of edges on the surface of a tetrahedra, or multidimensional tetrahedron, right? So maybe I'm not writing this complex nicely, because what's really happening is that the usual arrows are just going from K1 to K0, but the correcting terms will need to jump over 2 and then maybe over 3. And so they also have a shift in homological grading. So the total complex makes sense, and then it computes these things. So let me again mention that so really it means the fact that we don't need all operations of Maclaurin-Smith means that we could try to construct a similar complex which replaces cochains by an E2 algebra. Anything that carries these operations of the same style as Maclaurin-Smith operations, so we can be inserted into this, and then the expectation of this, and also to define these operations, I'm using not only a graph, but it's a planar structure on this graph. So maybe I want to even embed it into a plane, if that's possible, or just choose a cyclic order of edges coming into every vertex. So essentially, this structure, you can thicken the graph a little bit, and you will create a two-dimensional surface with boundary. And so if you do that, then for general coefficients A, which are not cochains, so I expect that this is related to factorization homology of this two-dimensional surface with coefficients in A. And so indeed, one version of definition of factorization homology is starting from the complex, which is of very, very similar nature. Right, and so once this differential gets corrected, so this is when this spectral sequence that was constructed by Bendersky and Gitler for computing the cohomology of this mapping space. Let me just write its first term. So it will be 0 to NP, CP, KR, and then there will be some boundary tensor product over the symmetry group. So there is, with when F is a field such as rational numbers, so real numbers, we take reduced cohomology, and then there will be tensor R, and then so for every P we have these terms, and NP is equal to the number of P simplices in KP. So Bendersky and Gitler have defined this spectral sequence, but with their definition, it wasn't really clear how to study differentials on that spectral sequence. And the approach that I was trying to explore is actually go back from the level of cohomology to the level of topological cochains, in which case one needs to work out this issue with non-commutativity and explicit repair by using Maclaurin-Smith operations. And so once we have things on the level of cochains, then again there are some conjectural formulas on what should be happening for the spectral sequence, but maybe that will be some other time. So I need to think through some of the formulas more carefully. Okay, so that's all I wanted to say for today.
Thank you very much. Let's thank the speaker.
Thank you.
Any questions? So I would like to kind of understand the lesson of this this construction. So for instance, if I want to understand the shifted tangent bundle of some projective variety and its cohomologies, what is this E2 algebra tell me about its cohomology?
So we know that on the level of cohomology for so if we have shifted tangent bundles would be related to which operad, to Pn operad with
yes.
So if we basically if we worked with objects which are maybe derived intersections of Lagrangians, then on the level of categories we would have to work with I guess maybe this is E2. I don't want to confuse E2 and E1. But basically, if you try to understand this monoidal structures or high monoidal structures on the level of categories, so you would have to say that you like with E2 algebras, you have a product and also homotopies between products both ways, AB and BA. And so you would, and these homotopies are realized by these Maclaurin-Smith operations. And so you would want to understand what does it mean on the level of categories. For example, what is the homotopy monoidal category? So which sort of operations on complexes of sheaves you're dealing with. And so the project that I had in mind, if this is understood, and this is several people are trying to clarify the combinatorics there. So can you try to approach your say quantum cohomology by saying that K is a sphere, and then you're maybe trying to
Exactly. That's why I'm asking. Seems like
to map
define quantum cohomology from it, because you're capturing some kind of V2 structure on the loop stack of that variety.
Yes. So the dream is to be able to take K as sphere, two-dimensional object, and thickening of a graph is a two-dimensional object, and basically say, let's look at maps from a sphere to a direct category, if you want, and then try to introduce just to study what should be cohomology of that mapping space, or something of the sort, and see if it gives any quantum cohomology information on a level from homological invariance that would bypass the geometry itself, or bypass as much as possible, because these additional operations on your category, they would have to reflect geometry in some way, right? But this is all. Yes.
Another naive really question. I don't even know. I can't see what happens. Why is it logically even wrong to start with graphs which have loops, or which have thick edges, or higher multiplicity edges and things like that?
I think multiple edges were originally introduced for geometric reason, that if you have thrown out the diagonal, if it happened once, you cannot throw it out again. So you don't know how to do double edge. But at the same time, once you have passed to this inclusion-exclusion thing, you don't mind that really. It just you're dealing with some kind of simplicial space. So your original goal was to start with a space, and then you throw out this union of diagonals. But now you say, okay, I'm working with a simplicial space, and maybe I'm not dealing with a subset of m to the n, but again, with appropriate understanding of which category you're working with and what you want to compute, the other graphs are not a problem. And in fact, there was a paper by Radmila Sazdanovich, who and maybe two co-authors. So they generalized this construction of Helmy, Guzon, and Wrong from graphs to simplicial sets of higher dimensions. So you could, if you have not just the edges but triangles, you could look at the triple diagonal, then xi equals xj equals xk. And so if you start throwing out triple diagonals, and again, you may have to understand this throwing out in appropriate category. So then you can go with arbitrary dimension. But then, of course, the expectation is that if your k is not a thickening of a graph, but thickening of a two-dimensional something, so it's kind of a three-dimensional manifold, which subsumes your picture. So then you may have to use E3 operations, and you may have to.
And what about the loops? The loops, if I want to do it for loops, then what? Then how should I think about it?
Well, if k is a graph,
so the graph has a loop, let's say.
Yeah. You can if the graph is a loop, then so first you take a circle, and one conjecture I didn't mention is that we expect that if you take a graph and you start subdividing it by adding vertices, then in the limit, this graph configuration space will have cohomology related to the mapping space. So yes, you can start with a graph actually eventually of any type. It's just that these differentials that we are considering, they are only dealing with subtrees, connected subtrees in this graph. But otherwise, there is no problem with just arbitrary things. And in fact, so some of this project was based on an earlier 2005 result, so which computed this graph configuration space with homology and related it to Hochschild homology. So this is around 2005 by Joseph Pshititsky. So he was looking at G, which is just a polygon with n edges, and then he said that he proves that as number of edges goes to infinity, so your earlier this graph configuration space has cohomology related to Hochschild cohomology. So this is what you would expect. Hochschild cohomology you expect to come up when you're studying the loop space, the visual loop space in topology. So from that point of view, it probably will work.
Okay, fantastic. Any questions from people in the room or people who are joining us online? From Vladimir? Okay. If not, let's thank the speaker again.
Thank you.
Thank you so much, Vladimir. And we will be informing everyone of the next seminar soon. Thank you, Vladimir. It was fantastic.
Thank you. All the best. Bye.